Okay, so here we are with the beginning of Unit 9, which is entitled Acids, Bases, and Salts. Let me just quickly run through these vocabulary terms to show you. First of all, you don't really need to know the definition for amphoteric. It's something they don't ask about anymore on the Regents exam. But I'm going to put a check next to the ones that you do need to know um, the definition for. And that would be, again, you don't need to know this one. You do need to know that one. All the ones I'm putting a check next to, you definitely need to know what they are. You need to know an indicator, neutralization. I don't really necessarily think you need to know the definition for pH scale, and you do need to know for titration. So those are the terms that you do need to know the definition for. Okay, let's move on. Okay, the objectives you already know. That's what you should be able to do once you have finished this unit. All right, so let's quickly take a look at the properties of acids and bases. One of the things you're going to notice is that in your reference tables, Table K gives you a listing of the formulas and the names of common acids. You don't really need to know how to name acids, and you'll see that later on in the unit. There's a whole section on naming acids and bases that we're just going to skip because it's not necessary anymore. They give you the names and formulas of the most common acids. One of the properties of acids that are dilute, meaning they're not very strong, they have a lot of water mixed in, is that they have a sour taste. And best examples would be fruits like lemons. Lemons have citric acid in it. Notice that lemons are, of course, sour. Acetic acid, which is vinegar, sour also. And carbonic acid, which is the acid that they put in sodas. Some sodas are very sort of sour tasting. Second is that concentrated solutions of acids, meaning acids that do not have a lot of water mixed in, are very dangerous because they can burn skin and eat holes right through your clothing pretty easily. Third one is that aqueous solutions of acids are electrolytes. Now, what does that mean? Well, if we take an acid like HCl and dissolve it in water, it will conduct electricity. And here's why. When you put HCl, which is technically covalent, it actually behaves like it's ionic. It actually splits into ions. Now, as we talked about before, covalent substances generally do not do this. Acids are an exception to that rule, so they behave like they're ionic. And the fact that it splits into these ions is what allows it to conduct electricity, because you need ions to conduct electricity. That's why substances like sugars, when they are dissolved in water, they don't split into ions. They do not conduct electricity. And the more ions in the solution, the better the conductor it is. So a weak acid, like for example acetic acid, this is a weak acid, is a conductor, but it is extremely weak. Okay, a stronger acid like HCl, which is right here, is a very good conductor because when it dissolves in water, it breaks apart almost entirely into ions. Okay, next, a couple of other things about acids and bases. Acids, anyway. Acids react with bases to form neutral solutions. When you have an acid react with a base, it's technically a double replacement reaction, but it's given a special name because it's an acid and a base and they neutralize each other. It's called a neutralization reaction, but it is a type of double replacement reaction. And here's a general template. You add an acid and a base together, they react and they form two substances always, a salt and water. Now the formula for water is always the same, H2O. The salt that forms depends upon the acid and the base that's mixed. So for example, if you look here, here's the acid, and we're going to go through later on how we know that's an acid, that's the base. Now what makes this a double replacement reaction is, notice the double replacement reaction, if you remember back from a previous unit, when you have two compounds, that's always going to be a double replacement reaction. And what happens is that the H and the Na switch with each other. So now the H joins up with the OH and forms water. It's H2O, but we write it HOH sometimes, but it's water, H2O. And the Na joins with the Cl. Notice that the Na is first, because if it's first on this side, it's got to be first here. This is the salt. And again, this salt is going to depend upon what acid and what base you have. The water is always going to be the same. Now the next one is has to do with table J. So what you should do is look at table J in your reference tables. And what you're going to notice is this is the activity series. It lists the elements at the top, which are extremely active, to the elements at the bottom. And what you're looking for is hydrogen listed on that table. Hydrogen is really all the way down at the bottom. of the table. There's only 3 elements below it: silver, gold, and copper, and there's a lot more metals above it. Now, basically, this reaction is going to take place if the metal that's by itself is above H2. Then the reaction will occur. So Na is all the way up here on table J. So what happens is the Na and the Na will kick the H out and form NaCl, and then the H will be by itself. Notice it's a 2 here because it's one of the Brinkelhoffs. This is an example of a single replacement reaction. You have a compound along with an element. It's a good review of the chemical equations we talked about earlier. So again, if the metal is above H, if the metal is here, the reaction will occur and it will be a single replacement reaction. If it's down here, meaning if it's copper, silver, or gold, that reaction, these will not react with a metal. So those are the single replacement reactions. And that'll be it for lesson number 1.